Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 18 on a simple ODE.
In this lesson, we're going to do one thing, and one thing only. We're going to look at a simple, single differential equation. Consider some of its many applications.
This is the subject of today's lesson. dx dt equals a times x, where a is a constant. This is a linear, autonomous, ordinary differential equation. It is extremely important that you know this and its solution. X equals the initial condition, x naught, times e to the at. What does this solution mean? What does it look like? Well, at time t equals 0, it passes through x naught, the initial condition. What it does from there depends on a. If a is positive, then you get what is called exponential growth. You get an exponential function in t that is growing as t increases. On the other hand, if a is negative, then you have exponential decay, where the values of x are getting closer and closer to 0 over time. Much of the importance of this equation comes from its ubiquity in modeling processes. You may have seen this equation used to model radioactive decay. If you look at, say, the radioactive isotope of carbon, carbon-14, then the amount I of that isotope changes to a degree that is proportional to I, where that constant of proportionality is negative. Likewise, if you look at the amount of a drug or medicine that is in a body, this changes over time according to the same differential equation, though perhaps with a different constant of decay. Both of these have negative coefficients and thus connote an exponential decay. There are some situations where you have exponential growth, however. If we look at the most simplistic model for population growth, one in which the size of a population, p, changes at a rate proportional to p. That constant of proportionality is a birth rate. This doesn't work so well for modeling human populations, but for certain settings, it's reasonable. On the other hand, continuously compounded interest is a fairly realistic model, at least in the short term. It says that the rate of change of the amount of money you have invested is proportional to how much is there. What is that constant of proportionality? Well, that is an investment rate. But what do we mean by continuous compounding? Let's assume an annual interest rate of R and an initial investment of money at time 0. If we were to compound our interest yearly, then after 1 year, the amount of money we would have would be our initial investment plus that initial investment times the annual interest rate. We could write that as the initial investment times quantity 1 plus R. If, however, we compounded that interest monthly, then what would we get? After 1 year, we would have the initial investment times quantity 1 plus R over 12, which is how much we would earn in January. Then we would multiply all of that by quantity 1 plus R over 12. At the end of February, we would continue on until the end of the year, giving another factor of 1 plus R over 12. That means at the end of the year, we would have the initial investment times quantity 1 plus R over 12 to the 12th power. That's actually a little bit more than we would get from an annual compounding. Now, of course, monthly compounding is maybe not so accurate because they have different days per month. So we could do it daily and get the initial investment times quantity 1 plus R over 365 to the 365th power. I think you can see where this is going. If we take the limit, then after 1 year, we get the initial investment times the limit as n goes to infinity of quantity 1 plus r over n to the nth power. Now, I know you've seen that limit before. You may recall that it is, in fact, e to the r. This is a hint that the standard linear differential equation is really behind what's happening in continuous compounding. Let's see how that falls out. If we look at the amount of money at time t plus a small increment, 1 over n, then, according to our previous reasoning, this is the money at time t times quantity, 1, plus r over n. And what we want to do is compute a limit as n goes to infinity. Now let's change variables a little bit, and instead of looking at n going to infinity, let us replace 1 over n by h, where h is a small amount going to 0. Then the amount of money at time t plus h is, from the above, the amount of money at time t times quantity 1 plus r times h. And now, expanding out that multiplication, we see a familiar sight from our definition of a derivative. The coefficient in front of the h term tells us the derivative of the amount of money as a function of t, and so we can see the differential equation. d dt of the amount of money equals r times the amount of money. That is our standard differential equation. Now, there are many applications of this equation that go far beyond radioactivity and population and money. Let's look at an unusual one coming from linguistics. If we read English poetry from antiquity, we'll see some unfamiliar words. If you look at Chaucer, the Canterbury Tales, many of the words are unfamiliar to us. But if we move the clock ahead to Shakespeare's time, then some of that poetry is familiar, some is unfamiliar. Moving ahead a little bit further to Milton, things are still a little obtuse, but more of the words make sense, and we could keep going with Blake and others. What we might guess is the following linguistic model, namely that the number of words in English remaining in common use decreases at a rate proportional to the remaining words. That means that words fall out of use. But this model states that words fall out of use according to a linear differential equation, where W is the amount of words remaining in usage and alpha is a decay constant.